Sari, and I am one of the museum co-directors. It's with great pleasure that today I get to introduce to you to one of my favorite geologists of all times. She has a bachelor's degree, a master's in geological sciences, and she completed her PhD in the Department of Earth and Planetary Sciences at Rutgers University. She's also a great friend, and since 2009, she has been working as teaching faculty and museum director. So she's also a great colleague, and all the team, I'm speaking for everybody in the team to say that we are super excited to introduce to you Dr. Lauren Adamo. So have fun, enjoy the next hour, and with further ado, here is Dr. Adamo.
All right. Am I unmuted? Okay. I can't see everyone, so someone stop me if you can't hear me. Okay, so thank you, Patty, for introducing me. I'm usually the one introducing these presentations, so it's fun being on the other side today. So I'm going to talk to you for like the next 20 to 30 minutes about geologic cores, which is one of my favorite things. It's something I studied for my master's and PhD thesis and dissertation, and something that I work on still with graduate students and undergrads using sediment cores. And we'll talk about that in a little bit. So a little bit about me. As Patty said, I am the co-director of the Rutgers Geology Museum, one of my favorite places. You can see that picture of me with my favorite fossil from the museum, which is our Mastodon. And some fun facts about me. My favorite dinosaur is the Triceratops. And my favorite minerals are mica and garnet. I'm not sure why I like those ones too much. They just
Lauren,
appeal to me.
Can you share your screen? We cannot see the slides.
Oh, I'm sorry. Hold on. Sorry about that, guys. I think I'd have this down after being all right, can you see my screen now? So this is where I was. Okay, sorry, take two. So there's the picture of me, if you didn't see it before, with my favorite fossil, which is the Mannington Mastodon at the museum. So when we are on the other side of this and we open back up to the public, I hope those of you who can will come see our Mastodon there. Okay, so introduction to core. So first of all, what is a core? And you see there's a picture of me many years ago on board a ship, and I'm prepping a multi-core. You can see the tubes here with my screen. Okay, I'm highlighting them. And there's a bunch of them around there, about 6 of them around that thing in the center that goes down and collects very, very short cores off the bottom of the ocean floor. So a core can be any cylindrical section of some sort of naturally occurring substance. So you can take cores of lots of different things, of bones, things like that. But in my case, I'm talking about geological substances. So things like sediment or rock or trees or ice. There's a variety of ways in which you can collect the cores. I'm not going to go into all of them because that is a topic all of itself of how coring is done on land, on the ocean, on big glaciers, things like that. So there's a lot of engineering that goes into the coring process. But there's definitely lots of different ways depending on what type of sample you're trying to retrieve. So one of the types of cores that geologists or people who are reconstructing climate can use are tree rings. And you can see these pictures here are all tree ring cores where when they take tree rings, they don't want to cut the tree down or kill the tree. So they take little borings. You can see they look like little pencils. They're a little bit longer, but they are long samples of the tree rings within the living tree. So if you're using trees, fossilized trees or trees that are already dead, you can do different types of process, but this is the process that's used in living trees so that you're not destroying the tree to recover the core sample. So another type of core are sediment and rock cores. So you can see this is a very short sediment core, just, a couple inches here. This is a rock core from the bottom of the ocean. And then this is a picture of a sediment core. You can see it's all mud and little fossils and stuff. So this is actually a photo of one of the cores that I study that are taken from the North Atlantic Ocean. So this is the work I do with these type of cores. They might not be too interesting to look at because they're just gray mud, but there's a lot of different things you can find by looking at the properties in those sediment down core. And you can see those little holes. Those are where I have taken samples out of the core so that I can analyze them in the laboratory. Another type of core are ice cores, and these can be taken any place where there is a glacier. So this can be like continental glaciers or mountain glaciers. But when ice cores are taken, because it is a very expensive process, because you have to get to these very cold remote places, and then you have to get those cold cores back to your lab in a still frozen. So they're not done just anywhere. They're done in places where they can get the best record. So a lot of them come from Antarctica or Greenland and specific places there. But there are cores taken from mountain glaciers around the world. And this picture here you can see is cold storage, where it is basically a giant freezer where these cores have to be kept. This is actually a picture of me inside one of these giant freezers, and you can see the people behind me all bundled up as well, where it can be 40 below in the freezer, and this is where you have to do the work on it. And then this picture here is a close-up of an actual ice core, and those little circle things you can see are actually air bubbles that are trapped in the ice, and that's something that paleoclimatologists and geologists analyze those air bubbles to figure out things about the past. But again, that's also the topic of a much longer talk, but maybe we'll get someone to talk about ice cores in the future. And finally, again, this is not the only place, but you can also get cores from the moon. These pictures came from NASA. So recently, I'll point out this person here, Dr. Julie Gross. She's currently working at NASA. She's a professor at Rutgers. But she is one of the team that was brought to Houston to open one of the Apollo core samples that was collected on the moon 50 years ago. They kept it vacuum sealed for the last 50 years, and that they just opened it now or last year so that they can analyze it with the new technology that has evolved since these cores were collected 50 years ago. So this picture here, you can actually see the three women who were responsible for opening this core. And this is just a picture showing the differences in the techniques between the 1950s and today. So you can see that they're going to get a lot more information out of this today since technology has advanced so much. This is just another picture from Dr. Gross. This is actually what the core looks like under vacuum, and then the three female scientists who were involved in this historic event. Okay. Actually, I left my life core right around there. Let me go grab it for you for a second. All right. Sorry, I was so worried about my sound for this presentation, I forgot to get this. Okay, so this is a activity that you can do at home, and I put the link there to this activity, but you can find it by searching School of Ice at Dartmouth. This is an activity called Life Cores. So when I went to this workshop where we were given these tubes, and we were told to tell the story with these tubes of how we got to that that webinar, that series that we were at. So this is the one that I made, okay? And so I filled it with pictures from my childhood, pictures of me doing geology with my family, going to Rutgers for my school, rocks and minerals and fossils to represent my time at Rutgers studying geology. Actually, this is a sample from the bottom of the ocean. This came from a core when I went out to sea to collect samples. And then I've got more fossils and some dinosaurs representing my time of getting to the Rutgers Geology Museum and becoming the director there. So what I'm showing, this core, the core of my life, tells the story of the events that happened in my life over time, of how I got to a certain place. And just a couple of things, these pictures aren't the actual events that happen. So clearly these pictures are not me actually going to these places of geology when I was little, but the pictures represent that time of my life. Same with these rocks. The rocks are a representation or an approximation for that event in my life. So if you've heard the word proxy before, proxy is a term that we use when we're studying cores, that we use some sort of sample or indicator or measurement to stand in as an approximation for an event that happened in the past. So I'm using these rocks as a proxy for my time I spent studying geology in college. So this is something you can do to make your own life cores, okay? And I just want to point out another thing is that with the cores, the oldest events, so the events that happened first in my life, would occur at the bottom of the core, okay? And the more recent events would occur at the top of the core, okay? So keep that in mind when we go through the next thing. So this is another activity that I want to walk you through. The same thing. So if you're a child, or at home, or a kid, or whatever, or a parent teaching homeschool right now, if you were to make a core of using emojis, so that your emojis are your proxies, okay? You're using an emoji to represent an event in your past, okay? So if we use the emojis that were here to come up with a timeline of what happened during a day, it might look like something like this, okay? Where you're using the coffee cup to represent when you woke up, the donut to be your proxy for the event of you eating breakfast, went to school. Well, in this case, did schoolwork at home. Maybe you did art, and then you ended the day playing video games. So again, this is a representation of what happened during your day, okay? So this represents one day of events. So what I mentioned before, okay, about the oldest events always being on the bottom and the youngest events being on the top. So if you go back to here, remember your first event, your oldest event of the day, whatever happened first is always at the bottom, and then the last event of the day is at the top. This is actually a principle of stratigraphy that we call superposition, okay? And so this is illustrated with these jars of sand where the oldest sand is deposited first, and then this orange sand is deposited next, and then the youngest sand is deposited last. And so this means that the oldest layers are always going to be on the bottom, and the youngest layers will be on top. This is a really important concept because it helps geologists to define how events proceed in cores. So this is just the definition. The oldest is on the bottom, youngest is always on the top, okay? So if we go back to our emoji core, here's our day one of what happened in a core, all right? So if we had a really long core, we could continue this with emojis to see what happened in day two. So again, here's day two. So day one, we played video games, we ended with going to sleep. We woke up again, we ate breakfast again. Maybe we went for a bike ride before we started school, then we had other events and we went to sleep. Okay, so that's one person's day. So that's our core one of one person's events in their life. So core two, let's see what if someone else did this, maybe a sibling or a friend nearby and made an emoji core to represent the events in their life. It might look like this, okay, where they woke up, they ate breakfast, but maybe they're eating something different. Maybe they went for a walk with their dog. Maybe they weren't feeling well. They watched a movie, played video games, went to sleep. And then the second day, you can see the events here. All right, so why am I doing all this with emojis? Well, what these are showing are several core geologic principles that we use in order to unravel the events that have happened in the past, okay? So first of all, we can correlate events between cores. So we go through separate cores at different locations, or in this case, we have two people's cores, and we look for events that are the same and that occur at the same time. So in this case, we're correlating this waking up with this core. That's the same event. You guys both people woke up and ate breakfast at a time. Okay, and then again, we see another correlation of events right here, that these are the same across two locations. Okay, and there, and there. Okay, the other thing that I want to point out is that you can also see cycles in cores. So for example, for when you wake up and go to sleep, that's one cycle, and then that cycle repeats. You wake up and then go to sleep, and it repeats again. So these are things that we can observe in cores so that we can start to make sense of these rock layers, or layers of sand, or layers of mud, or layers of fossils, or layers of ice. We look at the proxies, and so these proxies are not emojis, they're not toys or pictures like I have here. They are chemical signatures like isotopes. They might be, isotopes of lead or uranium or oxygen or carbon. They might be a certain amount of a particular sediment. So for example, in my cores that I study, I look for periods in the core where I have a lot of little pieces of sand. And these are what we call IRD, stands for ice rafted detritus. And so this is basically particles of sand that are brought to the deep ocean through the melting of icebergs. So I look in different cores from different locations, and I try to match up these times where there might have been a lot of this ice rafted detritus being brought to the ocean by glaciers. So if you can do this in multiple locations and use multiple proxies, you can start to unravel what happened. This is, an example of how we could do this with an actual core. I'm not going to go through what all these means, but all I want you to see, pay attention here, is you see the Q3A, and then here. The geologists who interpreted these cores interpreted this layer, there, as the same event. So again, you can see that the event might be different. It might be a different length or a different thickness at each location, but it's still the same event. And again, if you look here, this day one, this person looks different than this person's day one, but it's still the same cycle. So not only can we correlate events across different locations, but we can start to unravel how those events might be a little bit different at each location. Okay, so geologists do this with cores. They do this also with outcrops, so big things of rock out on the side of the road. They will go through and try to find these same events that they're looking for the cores. They'll look at the proxies to try to come up with a story of how things change through time. So what this is doing is something called relative dating, right? So when geologists talk about dating a rock or an age of a rock, there's two ways that they talk about it. They either talk about it as relative dating or absolute dating. So relative dating is when you say section A is older than section B, or section B is younger than section A. So this is using that principle of superposition, or there's several other stratigraphic principles, which I'm not going to go into today, that can also be used to help this. But the key for this is that we didn't place an actual age. We didn't put a number value. We're not saying that, section A is X amount of millions or 1,000 years old. We're saying it's older or younger based on its position and maybe some of the characteristics that we see in the rock than some other layer. Okay, and then the other type of dating is what we call absolute dating, right? And we will have a talk on this. Dr. Jake Satera will be giving a talk about the age of rocks and how we absolute date these layers a little bit later. So what you can see, the difference between this is that we actually use a numeric age when we talk about absolute dating. And this is through the process of radiocarbon dating or radiometric dating. And like I said, that will be covered in a week or so. So why do we care about cores? Why do we match up all these events? Why do we look at the proxies? Why do we use things like absolute and relative dating? Well, the whole point is geologists will put all this information together in order to come up with that story, to come up with what you're seeing in front of you. This is a very complex geologic timescale, but using all of those things that I just discussed is how geologists come up with these complicated graphs, how they know that the Cenozoic started about 65 million years ago. How do they know that these, how did they come up with these different time periods? It's because they've used the principles of absolute and relative dating and correlation of events through looking at many outcrops, many cores, things like that, to come up with this geologic timescale. So yes, that was a very quick and dirty overview of cores and different types of cores, and hopefully some of the bigger questions will be asked when we get to the geologic time one. So now I have questions that I'm going to go to. And yes, okay. All right, so I have a bunch of questions here about coring. So what is the longest core ever recovered? So this is something I didn't know off the top of my head. I had to go look it up. But according to some websites, the longest core that was ever recovered was, well, let's say, there's differences. It's, can you get how deep you cored, or is it how long you core? Because sometimes if you're trying to just get deep down, you don't worry about recovering the material that you're coring through. So the deepest borehole, the deepest they've ever drilled, was in Russia, and they reached about 40,000 feet into the earth. So that's really, really deep. And when it had to stop, because when it gets that deep, you actually, the temperatures and pressures inside the earth become so hot that the equipment malfunctions. So engineering hasn't figured out how to drill deeper than that yet. There's a goal to get to the Moho, which is the boundary between the crust and the mantle. We have never gotten there. We've only ever drilled in the Earth's crust, okay? Because it's just too hot. I read something, it was about 500 degrees that it gets to. So all the equipment just melts and malfunctions. So that's the deepest they've been. The longest cores that they've ever, recovered, some information said that they've drilled down like 5 miles long, or almost 6 miles long. That was a German program. So again, when we say longest core, it doesn't mean that there's a 6-mile thing of rock sitting somewhere. When cores are drilled, they're brought up into sections. So usually these sections are anywhere from like this big to about, a meter long or a meter and a half. So they're cut up into sections so that they can be stored more easily on shelves, and so scientists can study them later. So it'd be cool if there was a 6-mile long core, but we can't recover it in that way. Okay, so next question: what is the deepest core ever taken? I just said that went down to about 40,000 feet, just called the Kola Super Deep Borehole, and that core was only 9 inches in diameter. So it was a very thin core because they were more concerned about drilling deep into the earth. Okay, so how do scientists decide where to drill? That's a really good question. And it varies, and it really depends on what the scientists are trying to achieve. So if they are trying to study sediments that are, 100 million years old, they first have to know the geology of the area. So geologists have general geologic maps, so they know about how old things are in certain areas. So they'd have to limit it down to see, okay, if I can only drill this far down with a certain technology, I have to make sure that those sediments are, 20 meters from the surface. So if you want to get to 100 million years ago, and that layer is 5 miles down, you're probably not going to be able to drill in that area. If you want to get samples from the ocean floor that show a really good section of the last 20,000 years, so like from the last ice age, you want to go to a place where the ocean has accumulated a lot of sediments in the last 20,000 years. So some place where there would be a high sedimentation rate. And if you wanted to get really old sediments, you want to go someplace where there's a low sedimentation rate. So there is a lot of work and a lot of forethought that is put into exactly where people are going to drill. And it's not just they start drilling anywhere in the backyard. They do a lot of site surveys and things like that before they spend any money on drilling, because it's a very expensive process to drill. Okay, so another question, how do you drill cores from the bottom of the ocean? So there are a lot of methods. So when I went to sea, we were coring, not drilling. So there is a difference between coring and drilling. Drilling is when you have some sort of engineering thing that's actually turning and like drilling through the ground. Coring, you usually just have some sort of tube that's either like pushed into the sediment with a weight, or it's pushed in, it has a combination of weight and also maybe a piston that's sucking the sediments up into the tube. So to drill the bottom of the ocean, you have to have a ship or a platform. So like a drill rig, if you've ever seen pictures of how they drill oil in the middle of the ocean, you need some sort of surface where you can operate your machines from. And then you have the mechanics or the machine that has to go over the side of the ship or the drill rig, and it has to go all the way down to the bottom of the ocean. So you have to have a really, really long cable, and then it has to either drill or be pushed through the sediments at the bottom of that really long cable. So this is why scientists work so hard and so closely with engineers, because this would not be able to be done if you weren't using the geologists to figure out where to drill and using the engineers to figure out how to drill. So it's a very closely worked system to figure out that mechanic. So, and hopefully we'll have another talk a little later on in a few weeks about what it is like to actually drill cores from the bottom of the ocean. Another question, what is the longest ice core ever drilled? So from information I could find, that the US has drilled about 2 miles deep down into the ice. And I'm pretty sure that's in Antarctica, because there is actually 2 miles of ice in Antarctica. There's lots and lots of ice there, and Greenland. So I want to ask, how far back do ice cores go? Well, if you want to get a continuous ice core record, so if you're drilling and having, a record in the ice from the top of the core, which it would be today, all the way back down as far as it can go at the bottom, which would be the oldest event. So in Greenland, you can get back to about 130,000 years. In Antarctica, you can get almost a 1,000,000-year record, so about 800,000 years of a continuous record in ice in Antarctica. And the reason why you can't get them longer is that ice is actually viscous and it flows. So when you get farther down into the ice, the very bottom, like 2 miles down in the ice, it actually starts to flow out to the sides. And so the age of the ice gets a little distorted when you go deeper than that. So that's about as far as you can go having a continuous record. However, they have found pockets of ice at the edges of different glaciers in Antarctica that are almost 3 million years old, which is just crazy that they have ice that has been around for almost 3 million years. And that's because it flows, and when it hits like a mountain in Antarctica, it will flow up to the sides. And so on the edges of those glaciers, scientists can go and try to get little pockets of really, really old ice. So it's really cool that you can get 3 million year old ice. Okay, Mary from Scotch Plains asked, how do you date layers in a core sample? So there are a lot of things that go into it, and Dr. Satara will talk about the radiometric dating. So if you've ever heard someone say this rock is 65 million years old, how do we get that number on it? Well, that's through radiometric dating, where you use things like argon dating or uranium lead or a bunch of other ones. Or in younger rock layers, you can use carbon dating, but that only works for samples that are about 50,000 years or younger. The other way that you can date is by using that relative dating technique that I was talking about earlier, that you can say things are older or younger, but you can use that in conjunction with radiometric dating to kind of get an idea of how old things are. The other thing that can be used is the fossils that are found in cores. They give you kind of an age range. If you find certain fossils, like that we call index fossils, or we know these are species of animals or plants that lived, and so their entire lifespan or the entire existence from when they first evolved to they first died is only a couple million years old. If we find those in different cores or layers of rock, they can narrow it down to a smaller window of how old those things are. Mary also asked, how do you tell what came first in metamorphic rock cores? So I'm guessing she's asking, so if you have something that's been metamorphosed, and you're not sure, so metamorphic rocks, as we learned from the presentation a couple weeks ago, are rocks that have been altered through heat and pressure. And so there are other principles of stratigraphy, including one called the principle of inclusions or cross-cutting relationships. So there are other principles that help us determine which one came first. But it is also oftentimes hard to figure out the exact order of events if you have something coming and metamorphosing your rock and changing it all up. So in that case, if you had other places that you could look at to compare it to, that might give you a better idea, but sometimes you can't know for certain what the order of events are. It's a hard puzzle to figure out sometimes. Okay, so Mary also asked, in mid-ocean crust, are the cores more uniform than land cores? If you're talking about the crust, so the actual hard rock, no, things are very varied. I think with most science, things surprise us when you take cores or look at cores, or you start analyzing. It's very rarely what you expect it to be. There's these idealized cases of how it should look when we look at diagrams of what the oceanic crust and what the continental crust should look like. But very often is that case. The Earth is dynamic and there's lots of processes that can affect it, like faulting and metamorphism. You can have hydrothermal fluids going through. You can have diagenesis, which is just the alteration of rocks or layers of sediment through being buried deeper through pressure. That's I don't really have a good answer for that, but I guess my short answer is no, they're not more uniform because things are always changing. Another question, can you find fossils in cores? If so, what kinds? Yes, you can find fossils in cores. And what kinds, it really depends on where you're coring. So if you're coring in the ocean, you would definitely find ocean fossils. So in the cores that I work with, they look just like gray mud, but when you wash them up and you put this sample under a microscope, you can see that there's thousands and thousands, if not millions of fossils right there that you didn't see with your naked eye. So I work with a type of fossil, it's called foraminifera. They are a unicellular plankton that live in the water column, and they're the size of a grain of sand. So those are something you wouldn't see at first glance, but you would have to look under a microscope. You can also find any type of fossil, other like fossils you might find in marine sediments or any type of sedimentary rock, because the cores are relatively small. You're not taking a big piece of them. You might not be able to tell what the fossil is, but I mean, it's it's possible to get any type of fossil in it. You just have to be drilling in the right place. And I don't know the range of different types of fossils that they've found, but definitely possible. Okay, can you get climate information from rock and sediment cores in addition to ice cores? Yes, you can. So rock cores, you might get more paleo-environmental information. So geologists will look at rocks and try to figure out what the paleo environment was of what was it a forest? Was it, an ocean? So that can tell you climate data right there, what type of environment. And sediment cores, which is what I do, that's what my whole dissertation was on, is looking at the climate information by looking at the proxies of, either the chemical proxies or the sedimentological proxies to understand things about how the climate changed in the past. Another question, how are cores stored after they're taken? So it depends on what type of core they are. If it's rock core, that is obviously a lot more stable than things that are like mud or ice. So those can be stored in boxes. The mud that I study is kept when it's brought up off the ocean floor, it's in PVC tubes. And then those PVC tubes we take back to the lab, we cut them open, cut them in half. And then the two halves are stored in boxes that will keep them from drying out or hopefully keeping them from mold growing on them, which unfortunately does happen with cores. For ice cores, those definitely have to be stored in very, very cold freezers, because otherwise you'll have a puddle of water, not an ice core. Okay, in the slide that you were in the cold freezers with a big coat, how cold was it in the freezers? So it was about -30 degrees. Some of them are even colder. So usually the ones where the ice cores are stored are even colder, like -40. And then where you are doing the work, where you're looking at the cores or cutting the cores or photographing them, could be like 0 degrees, slightly warmer. So you definitely have to bundle up like you're going out in a blizzard. I was only in there for that picture I showed you. I was only in there for a little bit, but from previous years, I've been in there where I had hats and gloves and my face covered, and you have snow pants on. And I didn't put it in the presentation. I should have, where I have a picture of me in the freezer with my lips bright purple because it was so cold in there. So how long do you spend in the freezers working on the cores? So that's not what I do. I don't work with ice cores, although I think they're so fascinating. You can spend, a long time. Graduate students will sit in there and look at the core and count the layers in the core for long periods of time, but usually they'll come out if they get too cold and then go back in. So I know that when I was sampling my cores, I spent weeks of my life standing in front of my cores, taking samples and processing them. So it's probably equivalent for the people who are working on ice cores. Okay, so Samantha asks, how is it possible to date ice cores? It's a really good question. So sometimes there are events like volcanic events where a volcano will erupt and it will be a really big eruption, and that ash will get trapped. It will be blown around the world and it will fall down on the glacier and trapped in the ice. And if that happens, you can do some radiometric dating techniques on that. However, ice cores are super cool because it is one of like 3 things on Earth that actually records annual layers. So ice cores, tree rings, and things called varves, they are lake sediments, are the only 3 things that do this, that record a cycle each year that you can actually count back. So on ice cores, I encourage you to go look at some YouTube videos or look at some things about ice cores. When you take them back to the lab, you put them under a light source, a graduate student or a scientist will sit there and will count a layer. So 1 year in an ice core equals 1 light and 1 dark layer, and it has to do with the conditions being different in the summer and the winter. And so that cycle of 1 light, 1 dark is 1 year. And the same thing happens with barf sediments, which are mud from a lake. From the winter and the summer, it deposits a light and a dark layer, and that's 1 year. So you can go back in cores and count. And if you know what is the present day, what's 0, you can count back in time how old those cores are. And tree rings, again, most people know that a tree grows 1 ring for each year. But it's really unique that those are the only 3 things on Earth that do that. Okay, so another question. What would you learn from an ice core? So there's a lot of things you can learn from an ice core. You can see things of when, what the atmosphere was like in the past, almost 1 million years ago. So those little ice bubbles I showed you in that picture before, it's really cool because that is actually a real sample of what the atmosphere was like during that time. And it entraps that little tiny part of the atmosphere from 800,000 years ago and traps it in the ice. And so you can actually measure that and find out what the CO2 or what the methane levels or things were almost 1 million years ago. You can see how, different eruptions happen through time. You can see how like variations of dust being blown onto these things, and that can tell you things about, wet, dry seasons, like monsoonal frequency seasons and things like that. So there's a lot of stuff you can tell from ice cores. Samantha asks, can scientists see evidence of the tertiary extinction in rock cores? So if you are talking about the 6th extinction, which is the extinction we're probably in today, that's still too young of an event for it to be recorded, but we definitely see the extinctions at the end of the last ice age, and how that changed. So yes, we can see more recent extinctions. So tertiary being the time period, since the end of the dinosaurs. So yes, we can definitely see more recent extinction events in cores. Can you tell us what it was like spending time at sea? I loved it. It was very peaceful. It's a different perspective when you kind of appreciate how little you are in the grand scheme of things when you're on this boat and it's just water everywhere where you can see. I also tend to get motion sickness and seasick, so I had to deal with a little bit of that. But other than that, it was a lot of fun. I learned a lot. I got to see a lot of stuff. But when you're coring and doing these research cruises, you are working every day. But that's okay, because when you're on those things, you love it. Okay, so you're helping the scientists. You're collecting cores. You're collecting samples that are going to be run back in the lab later. So it was a lot of fun, and I hope I get to do it again sometime. Ria's mom asks, what's your favorite place to travel for geology? So a lot of places. I really loved Iceland. I was there last fall. That was definitely one of my favorite places I got to go. I loved Iceland because there's just so much different type of geology there. There's so many like volcanic geology and glaciers, which I really love anything to do with polar science, things about the Arctic or Antarctic. So I loved getting to be really close to the glaciers in Iceland. I did also spend a month in Switzerland 2 summers ago studying the glaciers there, and that was really cool too. And then I guess a third would be Costa Rica. I went there with some friends when we were all graduate students. We went to Costa Rica to go study be and see some of the volcanics there. So we weren't doing research. We were going to look there to look at the different volcanoes and learn about the different volcanic deposition places, and it was a lot of fun. So, any cores from Mars? Not yet. Well, that's not true. They have samples on the rovers. Again, if I'm saying this wrong, I apologize to people who do planetary stuff, but the rovers that are there on Mars currently are collecting samples, but we now do not have the technology to return those. So they are collecting them and just keeping them there for possibly some future mission that might be able to retrieve those things. But I hope that's not incorrect, and I apologize, Julie, if I said that wrong. Okay, another question. Yeah. Oh, okay. Julie just said no cores and no collecting yet. That's the next rover. Okay, so my Mars specialist, NASA specialist, says that it's coming. Okay, so if you find IRD in your core, what does that mean? Okay, so the IRD, like I said before, is the ice rafted detritus, and basically it looks like particles. It looks like sand. Maybe Ria or Julie, you can post a link to a picture of what this looks like in the chat room. But so IRD is brought to the ocean, in the deep, deep ocean, away from the continents. It's very hard for the big sediments to get into the deep ocean. So if you have big sediments, means anything big, like sand-sized or bigger. So if you find lots of like sand-sized particles, it has to get there by a certain way, and the only way that it can get there is through the melting of icebergs. And so what that signifies, when I find a layer that has a lot of IRD, the sand in it, it means that far away from where my site is, and most likely this is coming from Greenland, possibly Iceland as well too, that it's a cold time where there's the glaciers on these continents are growing, and they're coming to the edge of the ocean and breaking off into the ocean, melting, and then they travel in the water, and as they melt, they drop the sediment. And sometimes the sediment gets dropped very, very far away from its source, away from the continents. So when I find IRD in my core, it signifies that this is a colder time period where there's a lot of ice rafting of, and icebergs being made off of continental glaciers. Okay, so how deep is the Moho? So like I said, the Moho is the boundary between the crust and the mantle. And so the crust being the outer layer of the Earth and the mantle being the next layer of the Earth. And this boundary is not the same everywhere on Earth. And the reason for that is the Moho is deeper beneath continents and it's more shallow beneath oceanic crust, because oceanic crust is much thinner than continental crust. So beneath continents, it's about 22 miles down, and beneath an oceanic crust, it's about 4.5 miles deep. Okay, so last question I have here is, what made you decide to become a geologist? I've been asked this question a lot, and I can't put my finger on exact time when I decided. I know when I was little, I traveled a lot with my family. We went to a lot of national parks, and saw a lot of things like Mount St. Helens, Grand Canyon, Mount Rainier, things like that. And I just always found that stuff very fascinating and very interesting. And I always wanted to know I wanted to understand how those things were formed better. And then I remember learning about geology in school and learning about plate tectonics and finding them really interesting. And then when I was 4, 5, 6, that range, I told everybody I wanted to be a paleontologist because I wanted to dig dinosaur bones. So I I should have known that I was going to be a geologist when I was little because the signs were there. I was always interested in everything that had to do with rocks and features on the earth. So when I got to choose where to go to college, I knew I wanted to study earth sciences because I wanted to know more about all the amazing things the earth is capable of doing to make these features. So, okay, that seems to be the end of the questions. See if there's any ones that I missed, but so anyway, I think that's it. So thank you everyone for joining us for the session on geologic cores. And I hope you will be able to join us this Thursday to hear about the chemistry of the Earth, talking about some of the elements and minerals that go into some of the layers of the Earth that I was talking about today. So thank you, everybody. See you Thursday.